Welcome to another video. In this problem, we're going to find all natural numbers such that the sum of consecutive terms starting from 1 is equal to the product starting from 1. We just want to know how many terms you will get to before you no longer can have this equality. Now, the main idea behind this video is not to tell you what the answers are, because it is very easy for you to figure out what the possible answers are. It is how to show that beyond the answers that you get, you cannot get any other answer. And that's where math is actually difficult. It is you showing that there are no other solutions. And that's the main idea. Let's get into the video. So, if you've seen other videos where these notations are used, this is the notation for summation, and this is the notation for product. And what are we adding together? Well, we're just adding terms. So this can be written as, we're starting from I equals 1, then you go to the next I is going to be 2, and then the next I, and you keep going until you get to n, but we don't know what n is in particular. And the same thing for multiplication. So this one you're adding the terms, this one you're multiplying the terms. So this is what it looks like. So if you translate this, what you have is, you have 1 plus 2 plus, you keep going until you get to n. We're saying it is the same thing as 1 times 2 times, you go until you get to n. So we're saying, what are the possible values of n if this sum is the same thing as this product? Now, you know that a sum of terms is almost never equal to a product unless you're dealing with small numbers. Then you're able to say, okay, maybe. Now, that's exactly what we're saying. But just to make things more beautiful, we know there's a formula for the sum of the first n terms, like in an arithmetic progression, right? The sum of the first n terms, we know it. And then we know what the product of consecutive terms are starting from 1 all the way to n. This is what we call n factorial, and this is what we call the sum of the first n terms, which gives us the summation formula. We say that this is n into n plus 1 over 2. Remember? And this is n factorial. So the question may have been presented like this from the beginning, but just so you understand what this notation means, that's why I've written it in 3 different ways. Okay, now what are the possible values of n? Well, it is easy to start from n equals 1. Okay, so my claim is, if you start from n equals 1, it is true when n equals 1. It is not true when n equals 2. And it is true again for n equals 3. And it is not true when n equals 4. And it is not true when n is 5 or 6 or 7, and will never be true. Now, that never be true is what I'm going to prove. So I'm going to start with n equals 1 and claim it is true. Let me just make my claim. Claim n equals 1 and 3. Those are the only times it will be true. And I can show you that, because when n equals 1, let's do it. Okay? For n equals 1, we have 1 times 1 plus 1 over 2 equals 1 factorial. Is this true? Well, this is going to be 1 times 2 over 2, which is 1 is equal to 1. So my claim is true. Okay? Now, if we try for, it is not true for n equals 2. For n equals 2 will be equal to 2 factorial. Well, this is going to give me 3 equals 2. 2 factorial is 2. They're not equal, so it doesn't work here. Let's try for n equals 3. What we have is 3 times 3 plus 1 over 2 equals 3 factorial. Well, we know that this is going to be 3 times 4, 12. 12 divided by 2 is 6. 3 factorial is 3 times 2 times 1. It gives us 6. This is true. When we do n equals 4, it is not true. Well, that's my claim. Okay? And it's not true for n equals 5 or any number in the future. Basically, you know that factorials will grow faster than addition, but we just want to show it by mathematical induction. So, claim. If n is greater than or equal to 4, then this is never true. Then the sum from I equals 1 to n of I is never equal to the product. So this is my claim. And this is what I want to show how to prove it. It's a little tricky, but if you're doing mathematical induction, this is something you want to learn. Okay? I got better at mathematical induction by just making stuff up and trying to show them. And this is a good way, especially when you have inequalities. Okay? So how do you want to show they're not equal? So this is it. Want to show that anything like this, say n factorial, okay? Because the right-hand side is n factorial, want to show that n factorial will always be greater than the sum of the first n terms, greater than n into n plus 1 over 2. So we're going to use this space to show that when n is greater than or equal to 4, this will always be greater than this. And we can show that using, let's say this is the base case. Okay, the base case is n equals 4. Okay, we say that n factorial is greater than n into n plus 1 over 2. Now, is this true? Well, you can see it because n factorial is going to be 4 factorial. So we have 4 factorial is greater than 4 times 4 plus 1 over 2, which tells you that 24 is greater than 10. Okay, so it is true for the base case. All we have to do is say, if this is true for the base case, we're going to assume it is true for any n that is greater than 4, and then we have to prove that it is true for n plus 1. It is true for any n. Remember what we mean by any n, it means n's that are greater than or equal to 4. Okay, so ignore the ones before it. Our induction starts from n equals 4. So at this point, what you're going to do is we will now want to show that it is true for n plus 1. Okay, okay. So want to show it is true for n plus 1. How do you show it? Well, you just have to say n plus 1 factorial has to be greater than, well, that is n plus 1 factorial has to be greater than, it will be n plus 1, n plus 2 over 2. This is what we want to show. We want to show that this is greater for any n. Do I have enough space? I think I can squeeze this one in here. Okay, so watch this. Here, notice that n plus 1 factorial can be written as n plus 1 times n factorial. N plus 1 times n factorial is what this is. We want to show that it is greater than this. But there's a very nice way to show it. We can just transport back to this inequality, the base case we already established was true, and say, hey, I'm going to multiply this by n plus 1, and I'm going to multiply this too by n plus 1. It's more like a translation of this. So I have multiplied this by n plus 1. It has to be greater if I multiply this also by n plus 1. So I've got n plus 1 times n plus 1. Nice. Over 2. Let's keep this one because this one has this. Let's go here. N times n plus 1 is going to be n squared plus n. Okay, so this is going to be n squared plus n. Let me just show you what that is. So here is going to be, because this is the only part that's different from this. If you can show that n squared plus n is greater than n plus 2, or at least equal to n plus 2, we're fine. Look, n squared plus n should be greater than n plus n. Obviously, right? And n plus n is greater than n plus 2. How do you know that n plus n is greater than n plus 2? Well, it's because n is greater than 4. Remember, n is at least 4. That's what we're saying right from here. That if for any n, we want to show that n plus 1 is true. And remember, our base case for n is 4. So the smallest n can be is 4. So 4 plus 4 is 8, is definitely greater than 4 plus 2. So we have shown clearly that this is greater than this and it's greater than this. Therefore, the original expression is greater than this final one. So I'm going to say this is greater than n plus 1 times n plus n. Yes, because I've removed one of the n's in the square. And this, what you see, is still greater than n plus 2, which is greater than n plus 1, hey, over 2. Don't forget that. N plus 1 times n plus 2 over 2. That's my n plus 1 factorial. And this is where we're going. I shouldn't box it, but I like boxing my final answer. That looks terrible though, but it's okay. Never stop learning. Those who stop learning, stop living. Bye-bye.